we've been talking about recursive algorithms, and so today we're going to talk about the time complexity of those recursive algorithms. So earlier in the semester, if you remember, we already talked about time complexity. We said that we could find the time complexity function by adding up the number of operations that would be needed to perform an algorithm. So let's look here at this example. I think it's one that we've already seen back earlier in the semester. So for this input, we're going to be input 3 sequences. So a sequence called A, so we'd have A sub 1, A sub 2, up to A sub n, and then a sequence B, B sub 1 up to B sub n, C, C sub 1 up to C sub n, and so those would be input. And then we're going to be assuming that all of the elements in those sequences are positive integers. So then here is this algorithm, and we could talk about what it's doing. It's basically finding the maximums of each sequence and then adding them all together. But let's just concentrate mostly though on the number of operations that it would take to go through this, and therefore what figure out what the time complexity function would be. So remember, we would start at the top and take a look at the first line. Here we have max A equals A sub 1. So we could say that's an assignment statement, so it would just be one atomic operation, right? But remember, we got to saying where, even though we can count, like if it's 1 operation, 2 operations, 5 operations, whatever, not all operations would take the exact amount of time. So it's not really so much important that we call it a 1 as opposed to a 2, but we could just call it just some constant. And as long as it's a constant, it doesn't depend upon n. In this case, n is the length of those sequences. If it doesn't depend on n, then we just say, yeah, it's some function. We don't care if it's a 1 or a 2 or a 5. It's just, sorry, did I say function? It's some constant. It doesn't matter if it's a 1 or a 2 or a 5. It's just that it doesn't involve n, so it's just a constant. So we'll just call this one B operations as a constant, okay? Then that loop, it starts for j equals 2, goes up to n. So how many iterations would we be doing? Well, we would say that's n minus 1 iterations. But then inside, for each iteration, how many operations? Well, we've got the checking to see if A sub j is greater than max A, and if so, then doing an assignment situation. But again, that doesn't depend on n, so we'll just call it some constant c. So then going on down, this next line we'd say, let's call it a constant d, and then here we've got another loop. There's going to be, again, n minus 1 iterations of the loop, and inside we'll say there's some constant. We'll call m this time. And then for the last one, we'll have, last little section, we've got, we'll say p operations for that assignment statement, and then n minus 1 iterations of the loop, and inside the loop, let's say there's q operations. And then at the very end, we will output the sum of these 3 numbers. So we would need to get the sum of that and then return that or output it. So let's call that R operations. So if we were to add all of that up, well, you could say our time complexity function could be something then would be look like this, where we have B plus, and then now since C operations are done inside this loop that goes around n minus 1 times, right, then we would need to take C times n minus 1. And then going on down, here's plus D operations. Then again, we have a loop. M operations are being completed n minus 1 times. So we multiply those together. and then P by itself, and then for the next loop we've got Q operations being done n minus 1 times, so Q times n minus 1 and then plus R. So that would be the beginning of our time complexity function, but then we would want to simplify it as much as possible. So we could first of all, get rid of the parentheses by using the distributive property. And then let's combine all the like terms. So combine the terms with an n in it. So we'd have like a C plus M plus Q in front of the n. But then also combine the other constants that don't, the constants, the ones that don't have an n in it. So basically we would end up with some function that's got some constant times n, because some of those terms have an n in them, and then plus just some other constant. And it doesn't matter if that constant is 100 or 1 in each of those boxes. It doesn't matter. It's just because it's a constant, and that's all we care about. So anyway, that would be then, could be our, so we might want to put f of n equals, something Sn plus t, or something that is just represents some other constants in there. Now, if we wanted to see, talk about the asymptotic growth, we would look and say, well, what would be the asymptotic growth of that? If we have a constant times n plus another constant, that would be theta of n, right? Remember, when looking for theta, we don't care about the constants. If we just find, basically, if it's a polynomial, we find that the highest degree of our variable, in this case n, so it's just n. So we would say that this is theta of n. So that's how we did it back then, and we're going to do the same kind of thing though now, but we're going to be doing it for recursive algorithms. So as I've already reminded you, the way we find the time complexity function is that we add up the number of atomic operations performed by the algorithm on an input of size n. And we'll call this, even though in the last slide we called it f of n, since it's a time complexity function, we usually call it capital T of n. So we'll call it that. Now, here's how we do it. Remember, we're doing it now for recursive algorithms. Remember, within a recursive algorithm, we have the base case, which is just what we have to get to then begin. We get all the way down to some base case, and then we can start returning things. So whatever that base case is, that we need to find a number of operations that are performed during that base case. And so, we would say, okay, if whatever the base case is, whatever the value of our n would be for the base case, count how many operations for that, and that would be what we would call this initial value. Okay, so we would have an initial value in the function. But then we would need to count how many operations are done for that the situation where it's not the base case, for when the algorithm is going to call itself. Okay, so for n greater than or equal to 1, assuming that the base case was for n equals 0, then for n greater than or equal to 1, then the value of t of n is going to be defined by a recursive relation. So what it means is it's going to be dependent upon, t of n is going to be dependent upon t of n minus 1. And so it ends up being a recursive relation. So this says here, the value is defined by a recurrence relation that includes the running time for the recursive calls plus the additional operations performed outside the recursive calls. So anyway, without an example, it might be kind of hard to understand, so let's look at an example. Here is an algorithm which was the factorial algorithm. And so its name is factorial. We input a number n If n is equal to 0, return 1. Otherwise, then remember what we did. We called the same algorithm on n minus 1, put that into something we called r, and then eventually we would return r what we just got for r times that number. Anyway, we went through it before, so hopefully it's kind of familiar to you now. So first of all, let's figure out what the initial value would be for this. So that would be for when we have the base case, and that's for n equals 0. So let's count how many operations are done during this base case. Well, so we would have two things being done. One would be to test to see if n really is equal to 0, and if it was, then we return a number. We return the number 1. So those would be two different operations. So we could count that as 2. Now again, they're back. I'm following what the book is talking about. They're back to using 1s and 2s instead of like B's and C's. Remember, the actual constant itself doesn't really matter. Only what matters is if n is involved in any of these terms, right? So anyway, they're going to go ahead and just call it 2, whereas if I was doing it like that last example, we'd call it B or something like that. Okay, but we'll say t of 0 is 2. Then, so that would be our initial value. Then, now we need to come up with this recurrence relation that will tell us, how many operations are done for input of n, of size n. So here we see that we're calling the same algorithm, but calling it for n minus 1. So the number of operations that would be involved once this is called, factorial of n minus 1, how many operations would that be? Well, we would call that t of n minus 1, right? Because it's the same algorithm and we're inputting n minus 1 instead of n. So this whole call right here is going to involve t of n minus 1. So we've got that much, but then also we've got a few other little things here, and up here it says plus the additional operations performed outside the recursive calls. So we've got a few other things going on here. So we'll count those up too. So they counted 5 here. 1 to check for the condition n equals 0. You might say, well, wait, didn't we already count it up here? But that's for when in the case where it actually is equal to 0. But even when it's not equal to 0, it still needs to count, to check that. So every time, no matter what n is, it's going to check. So it'll need to check that again. Then we have an assignment to r. We whatever we get back from this factorial n minus 1, that goes to r. Then we subtract 1 from the n so that then we can put it into the factorial function or algorithm. And then we have to take r and multiply it by n. And then we need to return that. So anyway, they added that up and got 5 there. So we would need to say then that the recurrence relation for when n is greater than or equal to 1 would look like this. T of n equals t of n minus 1 plus 5. Okay, so again, that's a recurrence relation. It's not giving us an actual number because we would have to go and find t of n minus 1 in order to get this final number, but to find t of n minus 1, we'd have to find t of n minus 2 and so on. So it's a recurrence relation. So it's not just an explicit formula, but t of n is going to involve a previous value, t as with a smaller input value. So anyway, this together, the initial value along with the recurrence relation, would be considered the time complexity function of this particular algorithm. Now, once we would get this recurrence relation, you might think, well, we would need to do something in order to change that recurrence relation into some explicit formula so that I can just plug in n and get a number instead of having this recurrence relation. So looking at this picture here, we would start with the algorithm and come up with T of n. That's recursive definition, and so here in the middle box, recursive definition of T of n, which involves the initial value and then recurrence relation. But then we would go a step further and get an explicit formula for T of n so that we could just plug n in and get the time complexity function. Well, the book at this point is covering just this first step, where we take the algorithm, come up with the recursive definition. And then it says something like solving recurrence relations, and getting the explicit formula. That is done elsewhere in the book. And I'm not sure where it's done in the book because I haven't seen it. But anyway, the point is we're not going to do that here. So we're not going to have to go that one step further and get the explicit formula. All we need to do is take a recursive algorithm and come up with the recursive definition of the time complexity. So that's what we're going to do in this section. So these would be some examples of recursive definitions of T of n. So, we have these here. Notice it's the value of T of n depends upon values of that same function T at smaller values, n minus 1, or for the second one, it actually uses the value of T at n minus 1 and n minus 2. So those would be some examples of some recursive definitions. These would be the explicit formulas where you just have a function we can plug in n and actually get a number. That's what we're not going to be doing here in this section. So we're fine with coming up with just the recursive definitions. So once we would come up with a time complexity function, we would maybe sometimes need to be able to simplify those relations, that recurrence relation, so that then we could do some asymptotic analysis. So for one thing, right here on this slide, we're talking about how if we have some recurrence relations that, for instance, this first one, if T of n equals T of n minus 1 plus 5, if we're interested in the asymptotic behavior, then we could replace everything except for the t's with the theta regarding the asymptotic growth. So for this first one, we just have, outside of the t n minus 1, we just have a 5. So we could say then that T of n would equal T of n minus 1 plus theta of 1, because remember, any constant is theta of 1. So we see that that 5 is a constant, so we would just add on the theta of 1. For the second example, besides the T of n minus 1, we have 3n plus 2. So that one, that little extra stuff, 3n plus 2, we would want to find the asymptotic behavior of it, and so that would just be theta of n, right? Because it's a polynomial and the highest degree of n is just plain n to the first, so it would be theta of n. So that's kind of some of the stuff that you need to do, which is fairly simple, just taking anything that's not involved in that t, the other little terms in there, and just reducing those to what they are in terms of theta. So additive functions of n can be replaced with theta notation. Now, the book talks about situations where maybe we've come up with some recurrence relations that involve floor functions or ceiling functions. I'm thinking you might be familiar with the floor and the ceiling. So here in this box you see t, and then inside the function we have n over c, but it's like square brackets, except that the bracket on the bottom is not doesn't have a bottom, it's just at the top. That would mean that we're talking about the ceiling function of that, meaning we would take n, divided it by c, and then get the next highest integer. And then the next one here is where the top of the bracket is missing, so that is the floor function, and that would be taking n divided by c and finding the next integer lower than n over c. What they're telling us here is that if we end up, and I'm not sure that we would ever, in any examples that we do here in this class, that we would end up with terms like this within our recurrence relations for time complexity. But if we would end up with some terms like this with floor functions or ceiling functions, the book says that those values, the values of t at some value given to us by a floor function or a ceiling function is just the same thing as if we would just drop the floor or ceiling function and just look at the n over c. So terms such as t of the ceiling of n over c and t of the floor of n over c can be replaced with just plain t of n over c for any constant c. This seems a little random, right? Why are we talking about the floor and ceiling functions? It just turns out, since we're not doing all of that work to try to go from our recurrence relation to an actual explicit formula, they're giving us some existing recurrence relations and having us simplify them by using different rules. So this is just one of the rules they talk about, and so we're going to use that when they might give us something that has these floor and ceiling functions, and then you just need to know how to simplify them. Okay, so that's just something that you would need to know. So if we have maybe a recurrence relation that looks like this, that t sub n equals t of n equals t of the ceiling of n over 2 plus theta of 1, and theta of 1 probably came about because we analyzed those extra terms like we did above. If that was our t, we could more simply write it. We could write it more simply by just dropping the that ceiling function and just talking about t of n over 2 plus then the theta of 1. So we can just drop that ceiling function. The time complexity will be the same whether we include that or not, so we might as well not even include that ceiling function. Also, though, there's another thing that we have to know if we're going to be simplifying these recurrence relations, and that is constant factors in front of value of a t function can't be ignored. So you'll see what I mean here in a minute. But remember, up until now, when we look at constants, like, as terms up here, like the plus 5 in this first example, it didn't matter if that was a 5 or a 100, that would, simplify to theta of 1. And then the second example here, we have a 3 in front of the n. It didn't matter if it was a 3 or 100. Again, it just simplifies to theta of n. So we've gotten into the habit of just kind of ignoring our constants. And this is saying that we can't do that if we end up with a constant in front of a function value of t. So for instance, if I have this t of n equals t of n minus 1 plus theta of n, that's not the same. It's very different than if I had something t of n equals 2 times t of n minus 1 plus theta of n. We don't just drop that 2. So even though we would drop the constants when we're getting our theta for those extra terms, here when we have a constant in front of as a factor of some t value, we don't get to just drop that constant. Okay, so it's constant factors in front of a t value are important in the asymptotic growth, and so they cannot be changed. So we can't just ignore them. So we would need to leave them as they are. So there's some examples then that you have to do. I think you've got some participation activities to do, but also I figured you'd need a little bit more extra practice. So I opened up the solutions to some of these additional exercises, and they're pretty easy. So I think it would be definitely a good thing to look these over and make sure you know how to do them, because you might have to do something like that for the test. So for instance, on part A here, you would take everything that's not inside, the t function. So we have the 5n cubed plus 4n, change that to theta n to the third, right? Whatever the extra stuff is, find what the asymptotic growth is, and that in this case would be theta n to the third. So the 5n to the third plus 4n could be replaced with theta of n to the third. Here on part B, you see we've got n over 2, we've got the floor function plus t with the ceiling function. So each of those could be replaced just with t of n over 2. Drop the floor and the ceiling. But then we'd have two terms of t of n over 2. And so we would have to put those together and say that there's two of those. So there would be a constant in front of that t of n over 2. Then the 7n we would replace with theta n. For this third example, all you need to do is replace that t of the floor of n over 2 with just t of n over 2. And nothing else would have to be done. Now this last one here, you need to remember, maybe look back on that chart, because besides this term involving a function value of t, for this last problem, part D, we also have the 4n plus 6n log n. So you would need to look at those two terms together and think back and look at that chart and see if you can figure out what that would simplify to. What asymptotic behavior does that have? And replace that with the theta version. Okay, so you need to do that. Then there's also some examples in the additional exercises for where you're given a recursive algorithm and you're supposed to come up with the recurrence relation that would describe the time complexity. So these are also some problems that would be good for you to look over. And again, I have those solutions opened up. So at the very least, just kind of take a look at the solutions and make sure that you understand how they got them. Otherwise, if you have the time, you could try to figure it out yourself first and then check the solution. So there's 8.1.3 that would be good to look at. And then 8.1.4 is another one, and 8.1.6 is another one you can take a look at. So take a look at those to just give yourself some extra practice.